right, moving on to implicit differentiation. So there comes a time in everyone's life in which we have to talk about non-functions. That time is now. No, we can't go back. So we have to do the previous section, and we have to do this section to be able to talk about the last section, which is derivatives of exponents and logarithmic functions. So even though logarithmic and exponential functions, they are functions, and they're inverses of each other. But we need to talk about implicit differentiation first to explain why the e to the x is e to the x all day long when you do the derivative. And just why the natural log of x is 1 over x all day long. So we have to do this first. Yes?
Isn't there like an imaginary graph about the origin for like logarithmic and exponential functions as well?
There's no imaginary. They are actually about the origin,
Oh.
give or take. I mean, if you graphed them,
But
there's no imaginary. They're reflections across the line y equals x. They're true. They're true yesterday, they're true tomorrow, true today. So if I tried to do this, I wanted to do the derivative of the circle. I wanted to find a line that is tangent somewhere on the circle. I'd have to choose one of the two variables and solve for it. So that means I'd have to do this baby twice, right? Because I have plus and minus. I don't want to do that. Do you all want to do that? That'd be a big no on that one, Ghost Rider. So what we're going to do is we are going to do it implicitly. We're going to do the derivative of x, like we normally do, and then we do the derivative of y, like we would x. So all the rules we learned for x are going to hold true for y. So as an example, if I wanted you to find the derivative, d dy, of y squared, it's just 2y. And this would just equal 2y dy dy, or just 2y. But if I did it with respect to x, d dx y squared, it's going to give me 2y dy dx. We're going to do derivatives implicitly. If you are doing implicit differentiation, the first thing you want to do is see if you can do it, just get it by x. If you can't, who cares? Who cares? Just do the derivative rules that you normally do and just slap on a y prime when you do the derivative with respect to y. That's it. Once you do that, you then just solve for y prime. Beginning and end of it. It's really not hard. The only thing you have to remember is to slap on that y prime or dy dx if you're doing it. So, I have to get comfortable here. I'm so self-amused. Okay, so I'm going to do implicit differentiation on A or B. Which one do you all want me to do?
No, B.
B has the product rule, so I'll do the product rule. You all will do A in a minute, and I'm going to do B. Okay, so I'm going to do implicit differentiation on B. So I'm going to do the derivative with respect to x of 1. I'm going to do the derivative with respect to x of 3x. I'm going to do the derivative with respect to x of 2x squared y squared. Okay? The derivative of 1 with respect to x is just 0 because it's a constant, so that we don't have to worry about that. So we get 0 is equal to. Now, the derivative with respect to x of 3x is just our usual rules, so it's just 3. When I do the derivative with respect to x of 2x squared y squared, this is a product rule. So the first thing I have to do, let me move this up so you're not having to look over everyone's heads, is I have to do the derivative with the product rule. So I'm going to do the derivative of this first. I'm going to call that u. And I'm going to call this one v. So u is equal to 2x squared. The derivative with respect to x is our usual. So u prime is going to be 4x. No issues there. When I do y, which is v, is y squared, I'm going to get v prime is equal to 2y dy dx, because it is with respect to x. Now, if you don't want to write dy dx each time, just write y prime. That's okay too. So if you don't like dy dx, just write y prime. Yes?
So anytime we take the derivative of y with respect to x, we have to put y prime after it?
Yep.
Okay.
Because it is respect to x. So the entire time you're doing this, so the question was, why do I have to put the dy dx every time? Absolutely. Because if you were doing y is equal to 2x plus 4, that y prime, when you do the derivative of 2, is you are doing the derivative with respect to x of y, and you're doing the derivative with respect to x of 2x, and you're doing the derivative with respect to x of 4. Well, this is dy dx on the left-hand side, and this is just 2, but we can write dy dx as just y prime. So up until now, we've kind of been lazy with our notation, but now it's kind of important to pay attention to the notation. So every time you're doing the derivative of y with respect to x, there will always be a dy dx attached to it, or y prime, whatever one you prefer to put on there. So if I do this derivative with respect to t, here, if I say I'm going to do this derivative with respect to t, so dy, the derivative with respect to t, d dt of 2x plus the derivative with respect to t of 4, I'm going to get dy dt is equal to 2 dx dt plus 0, because it is respect to a different variable. The only time you don't slap on a y prime or an x prime is when it's in respect to itself. The only time you don't slap on a y prime or an x prime is when it's in respect to itself, because dx dx is 1, but dy dx is not 1. Does that make sense? Yes, no, maybe? Yes, no, maybe? No, yes, yes, no. No response, we're moving on then. You all need to respond to me. Smile and nod, smile and wave, smile and wave. Okay, so going back to this, using the product rule, we have u prime, which is 4x, multiplied by v, which is y squared. So this is u prime multiplied by v. And then plus v prime, which is 2y dy dx. Now, if you have a tendency to lose that prime, instead of writing y prime, write dy dx, because you won't lose it. But if you have a tendency to lose y prime, write it dy dx. And then I'm going to multiply it by 2x squared. So what this is v prime, and what this is u. What I have now is, and we'll do this more tomorrow, what I have now is 3 plus 4xy squared plus 4x squared y dy dx. Okay, I'm going to stop. Look at the beauty of this. Look, it's so pretty. So pretty. I love my job. Math is beautiful. It's delicious.
Exams are celebrations of learning.
Celebration of math. Okay, I gotta do this everywhere. All right. So once we do this, we're so excited because we got the derivative. Guess what we have to do now that you're going to be more excited about? Solving for dy dx, because that's what we're doing the entire time. So now we have to solve for dy dx. That means anything that does not have a dy dx gets moved to the other side. Because every time we're doing this, we are solving for dy dx. We want y prime. We want the derivative of our function. Yes?
Why don't we just move the y at the beginning to the other side?
Because we couldn't. It was buried inside of an x with it. We couldn't just move. So the question was, Why didn't we just move this y part to the other side? Well, because there's an x attached to it. No. It's because it's squared. You're just stuck with it. Accept it. Now, let's move 3 to the other side, the 4xy squared to the other side. And so I've got, remember this thing equals 0. So I've got negative 3 minus 4xy squared is equal to 4x squared y dy dx. Now we just divide both sides by 4x squared y, and we're done. So dy dx, or y prime if you prefer, is equal to negative 3 minus 4xy squared divided by 4x squared y. And I walk away really happy. I'm just so happy because it's done. I'm just so happy because it's beautiful. It's actually kind of beautiful. All right. I'm going to try another one, and then tomorrow when I see you all are going to try those. So I'm going to do another one of these. Which one do you all want me to do? Look at that beauty of C. Isn't that pretty? Oh, it's so pretty. Okay, let's do C. So option A is I multiply this out, which is totally cool. Option B is I do the chain rule. I'm kind of leaning toward multiplying out because it's not a bad multiplication out. It's just a perfect square trinomial. It's not a bad multiplication out. If that was a power of 3, I would use the chain rule, but it's just a perfect square trinomial, so I will treat it as such. So I'm just going to rewrite this as x squared is equal to, it'll be my first term squared, so it'll be 16 x to the 4th, y to the 6th. I'm just squaring that baby out. Plus 2 multiplied by 4x squared y cubed times 1. So 8x squared y cubed. And then plus my last term, which is 1 squared. Yes?
Why can't we just take the square root of both sides?
Because you're losing pluses and minuses.
Okay.
So if the question is, when you do the square root of both sides, some side needs a plus and minus. And that means you're going to have to do the derivative twice. I don't want to do that. Not a fan. All right, so now we just do our derivative. I'm doing the derivative with respect to x everywhere. So I do the derivative of the left-hand side, so that's just going to be 2x. On the other side, I'm going to do first the derivative of 16x to the 4th. So that's going to be 16, and then multiplied by 3, or multiplied by 4, because that's the power on x. X drops a power, y to the 6th. And then plus 16, now I'm just working the first term on the left-hand side. Now I'm going to do the derivative with respect to x on the y part. So 16, the power on y is 6. Y will drop a power. I'll have a dy attached to that, dx. Oh, come on, this is pretty. Sure it is. And then, don't forget, I still have x to the 4th there. And all of that is in all of its glory is the derivative of that first term. Yeah. Yes.
It's for the second term, y to 6. You have to do it separately because math hates us. That's why I hate math.
What? Oh, okay. So she asked me if I could do v's and x's. So this here is v prime. This is u. This is u prime. This is v. Okay? That's just the first term.
We have to do product rule.
Twice. Plus, now I'm going to do that second one in all of its glory. 8 times, I'm doing this with respect to x, so 8 times 2, x to the 1, dx over dx, which is just 1, multiplied by y cubed, I'm doing the derivative of the second term with the product rule. And then plus 8 multiplied, now I'm doing the derivative of y. So it'll be 3. Y is going to drop a power, dy dx, or y prime if you prefer. I have a tendency to lose them, so I write dy dx. Multiplied by x squared. So what we have in all of its glory, and this is glorious, 2x is equal to 4 times 16 is 64, x cubed y to the 6th, plus, I don't know what 16 times 4 is. 16 times 6, what is 16 times? What is it? 96? So 96, thank you. Y, I'm going to do the x first. X to the 4th, y to the 5th, dy dx, plus 16 xy cubed, plus 24 x squared y squared dy dx. Anything with the dy dx will stay, anything without the dy dx will move. So quickly, this will end up being 2x minus 64 x cubed y 6th minus 16 xy cubed is equal to 96 x to the 4th, y to the 5th, dy dx, plus 24 x squared y squared dy dx. Multiply a dy, or factor out a dy dx on the right-hand side and divide, so your final answer is dy dx is equal to 2x minus 64 x cubed y 6 minus 16 xy cubed divided by 96 x to the 4th, y to the 5th, plus 24 x squared y squared. And that's your final answer. Have a great day. We will see you tomorrow.